position operator and the Hamiltonian, and that means you can write everything in terms of localized states, which are localized at where the position operator is. In 2 dimensions, you have 2 position operators, and basically all the fact that you can have topological systems is the fact that these position operators do not commute in the end. Okay? So you cannot diagonalize both of them. Okay, so the moral of the story is the following. So Zach and Michel basically, this is not entirely true, but it's almost true. Although it's, yeah, so this is, so if everything is a band representation, then you don't have topological states. And what is not a band representation, so this is the new thing, is topological. So let's find how to do this in 2 dimensions. Okay, so I'm going to just go through it, I'm just going to go through it on the board, on here. So I just do 2 dimensions with inversion. Okay? So you have this 2-dimensional lattice. You pick an origin, which is here at 1A, and the site symmetry. You again find the Wyckoff positions or the places in the unit cell which are special. And by special we mean which have a symmetry group that's larger than identity. Identity is always a symmetry group, right? So clearly the origin of this lattice where the atoms sit is a special Wyckoff position, because just like here, which I erased, its side symmetry group is inversion times no translation, yeah? And again, I can put S and P orbitals here. We're just going to find all the atomic limits of 2 dimensions with inversion. This is another, so if I look at 1D, this is obviously another, this is just the mid bond. S and P orbitals, inversion times the translation. This is just a 1D system in this direction. Inversion times translation in the y direction. Okay? Side symmetry group of this guy. S and P orbitals here. As I go to momentum space, I get e to the iky. Here I get to e to the ikx. And the last thing that's, the only thing that's 2-dimensional about this now, rather than 2 1-dimensional, is this guy here. This is inversion plus ax plus ay plus x and y translations. And I can put S and P orbitals here, but it has a different momentum space. When I induce into the space group, when I induce S and P orbitals from here, okay, which just means I don't have S and P orbitals here, but the charge can migrate there. You know, I can hybridize the charge and move it there, for example. So the charge, this is a special position that the charge can sit on, and it would sit here, or whatever. The bands of S and P orbitals here would induce this band representation. Okay, this is a 1-by-1 matrix. Yes. Not under inversion, right? Under inversion, you just have, you can of course have d orbitals, you have C4. But under inversion, a d orbital is the same as an s orbital. Okay, because it just has, so this is the full classification of everything. So when you say yes, you just mean? I just mean the representation with eigenvalue +1, thank you, yes. Yeah, I just mean the representation with eigenvalue +1, yeah. Well, but I mean, like, yeah, we're trying to find universal things here. No. Yes, but so you know, it's impolite to use d orbitals and s orbitals and you only have inversion. So it's different. And as a matter of fact, the bands that the chemist would get would actually decompose into these. So yeah, very good. Yes. But it's certainly not the lingo that yeah. Okay, good. So now we can go to the Brillouin zone and ask, what are these atomic limits? So we've classified all the atomic limits. There are 8 of them. S and P orbitals at 4 Wyckoff positions, 4 maximal weak opposition. If I put an s orbital here, or, well, there's no meaning to an s orbital here because the site or like somewhere in the lattice because the group is identity there. So there's no meaning to classify them by, right? This is the full classification of the atomic limits. Okay, so for example, I go to the Briand zone now, and I'm going to look at what this is really the induced band. So don't think of it as just one orbital. This is orbitals at each point induced into the space group. And I look at the atomic limit. And this is atomic limit. It's S at 1A. 1A weak opposition was the center, if you remember, right? It didn't have any phase. So in the lattice, this, 1A, 1B, 1C, 1D didn't have any phase. So s orbitals is plus in the whole Briand zone. P orbital is, sorry, I'm going to use the black thing, is minus in the whole Briand zone. Okay, S at 1B, it's got an e to the I kx. Yeah, so this is plus, but this is minus. Y is kx equals to 0, so it's still plus. This is minus. Yeah. So is it clear how to build this table? Up to here, to everyone, is it clear or not? If it's not clear, just say now, because it's very easy to explain now, but this will be very hard later. So this is the band induced from s orbitals at 1A weak opposition. And these are the eigenvalues that this band has in momentum space at these points in the Briand zone. And so now I'm going to the Briand zone. I drew the generic Briand zone with inversion. It doesn't need to be a square. Okay, so I drew the generic Briand zone with inversion. Okay, and S at 1A, it's a plus eigenvalue. It's a plus symmetry eigenvalue at site 1A, and it doesn't have 1A is here at the origin. It doesn't have any translation, so I'll have plus everywhere. P at 1A is minus, but S at 1B is just like in the 1D chain. It sits here, okay, in the middle. So it picks an e to the I kx. But e to the I kx doesn't give you anything at the gamma point and at the y point because both of them are kx equals to 0. But it gives you a minus 1 at the x point and the m point. Yeah? So is this clear what this means?
This Briand zone is, I guess, conventional. You have a 45 degrees rotation.
Doesn't matter. With inversion, you'll always have 4 points that are invariant under inversion. If you add some other symmetries, like C3, then some of these points will get identified and the eigenvalues would have to be the same. But all that will come out directly. Very good.
Is there an obvious reason why there are 8 but not 16?
Well, there's 8 symmetry points or 8...
8 atomic limits.
Yes. So I have 4 weak oppositions, 4 maximal weak oppositions, and only S and P orbitals, so 2 times 4. So yes, very good. So I only have, so with just inversion, if I have other symmetries, I can have more things. Because if I have other symmetries, my site symmetry representation can be bigger. I can have more site symmetry representation. But here, I just said, so we made the statement that, so this cryptic statement that I didn't prove, but it's true that all the elementary band representation, all the atomic limits can be induced from maximal weak oppositions. So none of these weak oppositions is maximal here because the group is just identity. There's only 4 maximal weak oppositions. Their symmetry group is actually all isomorphic to inversion. This is inversion. So and I can have only S and P orbitals on 2 of them. Yeah, very good. Thank you. So the same thing is if I, it's with inversion for a lattice in d dimensions is 2 to the d plus 1 atomic limits, and you can classify all of them. Okay, very good. Thank you. So these are all the atomic limits. And you notice something about the atomic limits if you look at them. You notice the number of negative inversion eigenvalues or the number of positive inversion eigenvalue in all the atomic limits is even. You can see it, right? All the atomic limits have eigenvalue even. So then I'm going to ask, well, let me say I have a system in 2 dimensions. I have some band here and some other band here. But this band here has in momentum space the eigenvalues -1, 1, 1, 1. Okay? Okay? I'm going to ask, say I have this band. I have to prove to you that this band can exist, and this is where the compatibility relations come in. This band can exist. I haven't proved, like, admit that it does exist. Okay? I have this band with inversion eigenvalues in momentum space at gamma x. Okay? And it's got this inversion eigenvalues, this band. Well, now you immediately see that this band has got an odd number of negative inversion eigenvalues. There's no way it can be just from eigenvalues represented as sum of atomic limits. So, moral of the statement, it cannot be represented as sum of atomic limits. It cannot be represented by localized orbitals. This band is topological. And actually, because of the Berry phase, we'll find out what topology is. This is a Chern insulator with Chern number odd. If you add time reversal, then you just double these indices, and this is the Foucault index for quantum spin Hall case. Okay? But the moral of this method is that this can be generalized for everything, not just this is. I just went through this example, but the algorithm is very easily generalizable by computer to every group. Okay? So this band is topological by definition now, because you cannot describe it in terms of atomic limits. And we're going to find out what type of topology does the band have. Okay? And we're going to prove that it's a Chern insulator. And then, depending on the time that I have, I'm going to go to 3 dimensions and show that there's not only this Z2 classification of the quantum of the 3 topological insulators is not true. There's these higher order topological insulators which make it really a Z4 classification. Okay, so, and I won't have time to go into something else that I wanted, but that's okay. So let's see. So how do we find out what, let me just redraw this in a smaller case. So let's say I have one band. By the way, because I have one band which this is topological, this band cannot exist by itself. I have to have another band, somewhere else, which is also topological, which is the valence and conduction band, whatever. Right? But this band okay. So now, considering the fact that we know the inversion Wilson loop or the inversion Berry phase, it's very easy to determine what type of phase it is. So we know this phase is topological, but what type of phase is it? Well, why is it very easy to determine what phase it is? Well, there's 2 lines in this Briand zone where the system goes from being 2D inversion symmetric, right? This is 2D I had 2D inversion symmetry here, right? To 1D inversion symmetric. Well, there's actually 4 lines, but let's just take 2 lines. So I want you to agree with me that this line, this is minus y, this line is a one-dimensional Briand zone of an inversion symmetric system. Yeah? And this line is also a one-dimensional Briand zone of an inversion symmetric system. Yeah? This line is not a one-dimensional Briand zone of an inversion symmetric system, because inversion symmetry sends you to this line. Yes? Okay, so these 2 lines are, does that make sense? Am I saying something trivial? Okay. So now what we're going to do is going to compute e to the I integral a dky as a function of kx. This is kx. So you take the Berry phase in the y direction as a function of kx. Yeah? And I'm going to plot it as a function of kx. So let's plot the Berry phase. So this is e to the I times 0, or 1. This is e to the I times pi, right? These are the eigenvalues, or 0 and pi, or 1 and minus 1, right? It's a unitary matrix, so it has to, right? It's defined in e to the I times something mod 2 pi. Okay, and this is here at kx equals to 0, and this is here at kx equals to pi. Right? Yes? Now, we said that at kx equals to 0, this is a one-dimensional Brillouin zone with minus and plus as eigenvalues, as inversion eigenvalues, right? So it's a one-dimensional system with minus and plus inversion eigenvalues. What is its Wilson? What is its Berry phase? So plus and minus inversion eigenvalues, or minus and plus. This is what, if I looked at it as one-dimensional system in this direction, where would the orbital sit if I looked? Would it sit here or here? It's at the 1c, right? So its Wilson loop eigenvalue is what? Huh? So it's this guy, yeah? Yes? If I look at this, now I move to kx equals to pi. These are called hybrid Wilson loops or hybrid Vanier states, or in any case, they're just really Berry phase. So if I look at kx equals to pi here, okay, the eigenvalues are plus plus, yeah? Where does at kx equals to pi, where does the orbital sit? What A? Right, so it sits, so the Wilson loop eigenvalue is this. So this is a p orbital here and an s orbital here, if I was to look at them as one-dimensional systems in this direction, yeah? So first of all, notice the angular momentum changes from p to s, and that's the first hint that it's a quantum Hall state. But also, you know that the Wilson loop is this and this here at these 2 points, the Berry phase, right? The Berry phase at kx equals to 0 here is minus 1, e to the I pi, and here it's e to the I 0. Is everybody clear on that? So by the fact that I have the Berry phase to be continuous, I don't have, this is a full, I'm computing the Berry phase of this fully gapped band. Okay? I haven't proved to you that it can exist as a gap band, but I will, given time. But given that I'm computing the Berry phase of a gap band, it's got to be continuous. So the only thing you can do, modulo wiggles, is this thing. Yeah? So if I compute the Berry phase here, it will have this value. Here, it will have this value. Blah, blah. It does this. Yeah? Do you agree? Okay. So now, let me just go to, again, from 0 to pi. So I'd go like this. Okay? So I plot the full Brillouin zone. Here for kx equals to 0 to pi, I'm going to go from kx equals to 0 to 0. Yeah? Yes? By inversion symmetry, this guy goes into this. Okay? At 0 it has to be. So it does this. Now, what does this look like in gen stock? This was one of the edge states, chiral edge states. Right? So she showed some Berry phases, and this is how one of the Berry phases for the Chern insulator looked. So there's just one, sorry, not a lot of them. So there's just one. So this is Chern insulator or quantum Hall with Chern number what? Or Hall conductance. How many edge states do I have? 1. Okay? Okay, so we've identified this phase as being a Chern insulator with Hall conductance 1. Yeah? Now, of course, actually, this is not entirely correct. Given these eigenvalue structure, you can only say that the Chern number is 1 plus 2n. Okay? Why is that? Well, instead of drawing this thing, I could have drawn this winding many times. The only things that I had, the only requirements was that the Wilson loop was minus 1 at kx equals to 0, plus 1 at kx equals to pi, and continuous in between them. But I could have drawn this. Okay? You see, as long as this is the same, this is e to the I 0, e to the I pi. I could have drawn this. Yeah? Etc. But you'll see that if I do this, then what's the Chern number here? Etc. So the fact that this is pinned here and here tells you that the Wilson loop tells you the Chern number can be 2n plus 1. Does that make sense? You can draw 5 times if you want. That's right. So this band, the moral of the story is you have a symmetry, and this symmetry can only tell you, inversion can only tell you the Chern number mod 1. But in a band that has these eigenvalues, plus, plus, minus, plus, you know it has to be topological. So it has to have a Chern number, or you know it has to have something topological. This band, by symmetry, you can identify as having an odd Chern number. And the reason why you can't identify it as having a particular Chern number mathematically is because you know this value of the Berry phase, this value. But the symmetry doesn't dictate what's happening here. It only dictates that what's happening here has to happen here too. So this is this inversion, right? And inversion just basically takes this, right? So it dictates, but it doesn't dictate what's happened here. So this value can be anything, which means I can wind it once, or I can wind it 3 times, or I can wind it 5 times. Physically, you can understand this from this statement that I've made, that this is a p orbital here, and this is an s orbital here. So the change in angular momentum as I go in the Briand zone is 1, which is the odd number, but really you don't make a difference. It can be p and d, so it can be change from angular momentum 1 to angular momentum 4 or 6. It's just angular momentum even and angular momentum odd. By angular momentum meaning really inversion representation. So this is the physical argument that it only tells you this. Does that make sense?
So
yes.
So there's ambiguity in the number of the edge states, right?
There's symmetry will only give you the edge states mod 2. Now, if you want to find the edge states, you compute the Berry phase. But symmetry is this is much easier to compute from first principles, because you only need to compute this point, this point, this point, and this point. Right? You notice how I knew what's happening just by computing this point, this point, this point, and this point, which are 4 points. To get this calculation, especially if you go to 3 dimensions, you need the whole Briand zone to get this Berry phase to see if it winds like this or like this. Right? So in other words, the full classification is not only eigenvalues, it's also Berry phases. But eigenvalues can immediately tell you if something is topological. If eigenvalues tell you something is not topological, then you still need to compute Berry phases to make sure there's not topological. But eigenvalues can immediately tell you something is topological. Does that make sense? Yeah. Okay, very good. Yes? That's right. So let's include time reversal. Very good. Let's just do it. So I include time reversal. I can't do it with one band. Right? Or if I wanted to do it with one band, this would be a semi-metal, because right, there was let's say spinful time reversal, right? So we go to topological instead. Spinful time reversal, I have Kramer's pairs. So there's no way I could have a band with just one negative eigenvalue here, because I would have 2 negative eigenvalues here. So this would be a semi-metal. So this Wilson loop wouldn't make sense, because I said you make the projector into a full set of bands. So if I want to induce time reversal, I had 2 here, plus, 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 plus. Okay? And this is a quantum spin Hall state by the Foucault criterion, right? You can just, okay, so how do we see it here? Well, if you induce time reversal, the only thing you're going to do is make the time reversal conjugate of this guy here, which is this, and this guy here, which is this. So this is the spectral flow that Jen showed for the quantum spin Hall case. Make sense? Okay, very good. Any other questions? So the moral of the story is not to reinvent the wheel here, but that this is generalizable by this induction procedure to everything, to all the space groups. Yes.
So if we have a symmetry of order, let's say P, right, then we can tell the Chern number in modulo P.
If you have a, that's right. So if you have C and symmetry, you can tell number modulo n.
Okay.
Just by comparing to the atomic limits. That's right. That's exactly correct. Any other questions? Yes.
So can I say that the Chern number is defined by some number of times of the angular momentum Chern?
Yes, but that's a colloquial statement because angular momentum doesn't mean very much, right? It's angular momentum mod the order of the group, you know, which is you know. So you can sort of say it like that, but really the Chern number, if you want to compute it, is just the number of windings of the Wilson loop, of the Berry phase. But symmetry will tell you, if I have this, I know this is topological state from symmetry, and this will tell you that the Chern number is odd. Okay. Okay. So now it's a very easy. So any other questions? Okay. So now I hope this example, which is by no means comprehensive, makes it very clear that now you can perform the following algorithmic search. You can take your favorite DFT program, and you can compute in a huge Brillouin zone of whatever 3D, however complicated the group is. You can compute all the elementary band representations, and these are 10,398 of them. Okay, so you can compute all the atomic limits. I mean, these are tabulated. Now you take your DFT program and you compute the bands, some set of bands, whatever set of bands you want. You compute the bands, and then you ask, can they be written in terms of atomic limits or not? And if they can't, like this one, they're topological. Yes. Okay, so you can do this program, and then you can ask the following question. For example, you can ask this question. You can ask, you know, if I have two different materials, how do I know if they belong to different topological classes or the same class? That's just a linear dependence check, and actually can be performed algorithmically, but just to give you the flavor, this is just a linear dependence check. So for example, say I have one band, which is given by these inversion eigenvalues, this band, minus, plus, 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 yeah? Not the doubled one, just this one, okay? This one, say it's given by these, okay? I claim that this band is equivalent in terms of Chern number mod 2 to this band, minus, minus, plus, plus. So this band, in terms of Chern number mod 2, minus, 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 plus, okay? So you ask, if I have material A and material B, how do I tell if they're the same topological class or not? And the way it is very simple. You check if material A plus can be written in terms of material B plus or minus some sum of atomic limits. So this is material A plus atomic limits. This is material B plus atomic limits. If I can get to the same structure, if I add them, for example, just in terms of eigenvalues first, then they're the same strong topological phase. And by strong, I mean also the colloquial weak topological states, which are just defined as, you know, obtained by layering. I include them in strong ones, which I don't have time to explain. But these are all the states that you know so far. So for example, for this one, you realize that this state, if I add an atomic limit, is equal to this state plus this atomic limit. Right? This atomic limit is s orbital at 1a position. This atomic limit is, what the hell was this atomic limit? It's plus, minus, minus, plus. Okay, this atomic limit is s at 1b position. Yeah? Because it took a minus when kx. Okay, so these are the same topological class. This topological class is just the topological index that you're used to, right? The Z2 indices. For example, this case, in inversion in 2 dimensions, which we just solved, you have 2 classes. If you have an odd number of minuses, inversion eigenvalues, that's class 1, obtainable by symmetry, which is just the same universality class as this guy, odd Chern number. And if you have an even number of minus eigenvalues, then it's class 2, and it's just an atomic limit, or a sum of atomic limits, yeah? And if you want to find more, the actual Chern number, not just Chern number mod 2, then you're stuck here. You have to compute Berry phases afterwards. Does that make sense? Yes? For example, in this case, it would be inversion eigenvalues. In other cases, other eigenvalues of whatever symmetries you've got. Okay, so most groups are not, this is symmetry group 2. They're not as simple as inversion, right? But you can always, this is an algorithmic process that you can always do. So the EBR has more than eigenvalues, right? So remember I had an e to the ik, right? So in general, this is a very simple group, right? But this is a very simple group. But this is, the EBR has this, e to the ik, right? This is the EBR, for example. This is the atomic limit. So it contains the eigenvalues at high symmetry points, right? Because you can go to k x equals 0 or pi. But it also contains this matrix structure between these symmetry points. In this case, the matrix is simple. It's just a number. But in general, it's more complicated. So for example, you can have 2 elementary band representations, 2 atomic limits. They have the same symmetry eigenvalues at high symmetry points, but they have different Berry phases. So they're different. So really, a state is topological if it's not continuable to atomic limits in both eigenvalues and Berry phases. I haven't talked about the Berry phases, but if it's not continuable in terms of eigenvalues, then you already know that it's topological. Okay? If, so for example, this state here, if I have a band that has this eigenvalues, okay? This, in terms of eigenvalues, is a EBR, right? This is S1A induced into G. Yeah? Okay. But I can't say, so this symmetry method would tell you it's trivial by the symmetry eigenvalues. Okay? But what the hell is that? But that's actually not, well, it's not true. It's incomplete because I could have, all that this is telling you is that the Wilson loop here at 0 and pi is 1, okay? Because this is s orbital and s orbital. So it's 1, 1. But you could have 1, 1 with this, okay? This is winding number 2. This is Chern number equals to 2. And this band would have a completely different structure than this e to the ikx here. It would be e to the ikx over 2, for example. Okay? So if the symmetry eigenvalues tell you something is trivial, you have to do further work. But if the symmetry eigenvalues tell you something is non-trivial, then you're done. Does that make sense? Okay. Any other questions? Yes?
So can you go to the next few slides where you define definition of material A with the
Yes, so this is the same as the topological index. And in fact, topological index can be obtained by a linear dependence code on this. Right? So you remember that all the atomic limits had an even number of minuses?
Yeah.
That's one class. An odd number of minuses is another class.
Yeah. I'm just wondering about what you mean by plus.
So you just write, so for example, can I get to, these are the eigenvalues at high symmetry points, okay, of this band, plus, minus, plus, minus, plus, plus, plus. And I'm giving you another band, which has eigenvalues minus, 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 plus. And I'm asking, are these bands the same in terms of eigenvalues? There's the same topological class in terms of eigenvalues. And in terms of eigenvalues, they are in the same topological class because one of them has an odd number of eigenvalues. The other one has also an odd number of eigenvalues. So you know, if then I prove it to you here that they're the same class because I can add to this band an atomic limit and obtain this band plus another atomic limit.
So you're defining the thing on the left-hand side by the thing on the right-hand side.
That's right. This is the same thing as a topological index. Okay, and you can obtain it. You can obtain it like this, or you can obtain it with some Smith form. Okay. How much more time do I have? 20 minutes. Oh my God. Okay. So first, so I want to prove two things and show you how to use compatibility relations. So I want to prove. So the leftover thing that I haven't proved to you is that this band can actually exist. Okay, so I said take a band that has minus. So I want to prove that, and I want to show you how to do higher order topological insulators in 3 dimensions very quickly. Okay, so I said I have this band, and it's topological, that has eigenvalues minus, plus, plus, minus. Okay? So the normal, sorry, minus, plus, plus, plus. So the normal thing to ask is, can this band actually exist, or are you just, you know, selling me a pipe dream? So the answer is this band can exist, and how do you know that it can exist? Well, you can build, without needing a Hamiltonian, you can build the structure of eigenvalues of all the bands that can exist in momentum space, all of them. Okay? So, for example, how would I do it? Well, there's 2 ways of doing it. So I'll show you an example where a band exists and where a band doesn't exist. With inversion, they all exist. Okay, whatever eigenvalues I want to put here, they all exist. Okay, so what's the fundamental principle? Well, now I want to find bands in momentum space, so forget about real space. Okay, this is a band that's not expressible in terms of localized atomic orbitals in real space because I found it to have odd number of negative eigenvalues, and all of them have positive, have even number of eigenvalues. So take this Briand zone, okay, and inversion is the symmetry that takes kx to minus kx and ky to minus ky, right? Okay, so in other words, inversion doesn't leave any other point invariant except these 4 points. You agree? Any other point, it changes to some other point. So how do you find the bands that can exist in momentum space? Well, what you say is, well, let me focus on these high symmetry points, which in this case are also called maximal k vectors. So you're asking how do I know the points that I should look at? In this case, they're just these 4. There's a set of maximal k vectors. Maximal k vectors means their symmetry group. There's no other group between their symmetry group and the space group, basically. Okay, so this is inversion, this is inversion, the space group is inversion. So these are the maximal k vectors. Now representations here in the wave function, there's 2 of them. At each maximal k vector, 2 of them possible. Okay, minus and plus. The minus one is the B representation. It's got this E is the identity operator. Forget about it, I just wrote it here. The minus one is the P in momentum space. Okay, so bands can act. This band here acts as a P band in momentum space. This band acts as an S band in momentum space. Okay, like P and S are just labels here, right? They're just 2 representations, A and B. Okay, so this is the B representation here. This is the A representation here, the A here, and the A here. Okay, in momentum space. Right? Notice how the symmetry groups, even though, you know, now I'm talking about momentum space, and before I was talking about real space, the symmetry groups are really, you know, just isomorphic to inversion. They're all, right, it's not, but they have different meaning physically in real space and momentum space. Okay, so here I call them B and A. B is this representation, okay? So now I ask, is there an obstruction to this band existing in momentum space? And the only thing I need to check, actually, is whether if I go on path connecting these points in momentum space, so this guy with this guy, this guy with this guy with this guy, there's an obstruction to connecting a B representation to an A representation. Okay? So it becomes pretty obvious very quickly that there's no such obstruction because the symmetry group of this guy here, of any point here, say point X here, or point Y here, whatever group, whatever point you want here, the symmetry group includes just the identity operator. Yeah? So when this band has moved from here to here, the identity operator is just one representation. Right? One irreducible representation. One. So when this band has moved from here to here, there's no labeling of B or A anymore. Okay? So for example, if I have A and B here, then once I move from gamma to X, then there's no, the moment I'm off from gamma, there's no, okay, this should be exactly the opposite. This doesn't matter, you're done. There's shit. Okay? The moment you move from here to here, you can connect them because they're really the same representation. You connect A with A and A with B. Okay? Now let me give you an example where you can't do it. So mirror symmetry. So say instead of 2D inversion, I had 2D mirror. Okay, so if instead of 2D inversion I had 2D mirror, then the following thing would happen. Instead of kx going to minus kx, kx goes to kx. Just ky goes into minus ky, right? So now I have full lines in the Briand zone that are invariant under mirror, not just points. This full line is invariant under mirror. And this full line is invariant under mirror. Mirror also has two representations, A and B, just like inversion had. But now the fundamental thing is that mirror is invariant under a line in the Briand zone. Or leaves a line invariant, not mirror. A line is invariant under mirror. Okay? So now I ask, can I connect representation A at gamma with representation A at X? Okay, if I just have one band whose representation was A at gamma and A at X, well, yes, because as I move away from gamma, since mirror leaves this line invariant, every point on this line is classified by A and B. So A remains A and can connect to the A and B. But consider the following thing. Can I have a band with A, representation A at gamma, so eigenvalue plus of mirror symmetry at gamma, but eigenvalue minus of mirror symmetry at X? Yeah? So I have A and B. This band cannot be connected like this. Why? Because as I move away from gamma, this A remains A representation. It's still got the mirror eigenvalue 1. And this B, as I move away from X towards this, towards gamma, this is the gamma X line, it remains B. Right? And there's no way I can make A into B while I keep the symmetry. So that means that at one electron, if I had this system, so by just knowing two eigenvalues at A and B, okay, at one electron per unit cell, this system cannot be an insulator. And it's a protected semi-metal. And I need to introduce, you know, another B and another A here. So the system has to have at least two bands by just knowing the eigenvalues below the Fermi level here. And now it's a protected semi-metal, and this guy is protected by mirror. Okay? So that's how you know, that's how you can classify all the bands in the Briand zone, and this is through the graph thing that John was talking about, all the bands in the Briand zone and all their connections. And actually, if you want to find if they're just connected or not, then there's an easier way as a null modes of some matrix. But you can classify, you know, is this example clear? And it's clear that it can be, you know, you can generalize it to any group because you know the maximal k vectors. If I have some representations there, I will be able to tell you how they, you know, decompose into representations of a line and how the other representations from the other point decompose and whether they can match. So I'll know how to build bands in the Briand zone. Yes? Yes? Sorry.
If you check all possible cross-sections, for the most general group that I have, I mean, not only gamma to X,
So there's a list of lines and planes in the Bilbao crystallographic server that also tells you what you need to check. You don't need to check all of them. There's only maximal k points, and those this is representation subduction, because you're going from a high symmetry group of points to low symmetry group of points. So you can check. It will tell you which points you need to check. So these are these things, which are basically plotted even. It will tell you which points you need to check, for example, for every. And of course, you don't do it by hand, because, well, actually, if you're Barry, Jen, and Zijun, you do it by hand. But no, like yeah. So you don't do it by hand; you do it by computer. Okay. So how much more time do I have?
You can end early if you want to, but you have 5 to 10 minutes. You have 10 minutes.
Okay. So let me just do something. Okay. So let me just tell you like a little bit about higher order topological insulators. So let's do 3 dimensions, since we're so good now at doing 2 dimensions. Let's do 3 dimensions with inversion. Okay? So 3D, but no time reversal yet. Okay? 3D with inversion. Okay? So I don't want to bore you, but you now realize that there's, 8 maximal Wyckoff positions, right? So I have cubes. My lattice is a cube. Let me just bore you. Lattice is a cube, and I have 1, 2, 3, 4, 1, 2, 3, 4. Yeah? Does that make sense? Okay. So, and I can put S and P orbitals on either of them. So how many atomic limits will I have? I have 16 atomic limits. Sorry? Okay? And what number of minuses of eigenvalues? So now I go so this is lattice. 1A, 1B, 1C, 1C, 1D, 1E, blah, blah, blah. Okay? So now I go to the Briand zone, which is, let's draw it as some parallelepiped. And I also have 8 points in the Briand zone. Yeah? 8 high symmetry points in the Briand zone. Right? 0, 0, 0, all the way to pi, pi, pi. Yes? What do you think, how many eigenvalues do you think the atomic limits will have? What do you think would be the number of eigenvalues? What will it come in multiples of? So atomic limits in 2 dimensions came in multiples of 2. Atomic limits in 3 dimensions come in multiples of 4. And you can immediately see that. And you can just write them down, okay? But you can roughly see that by realizing that on each of these, if I induce from here, okay? If I induce from this side, for example, it's going to have 2 negative eigenvalues at k z equals 0 and 2 at k z equals to pi. So the number of negative eigenvalues, also number of positive eigenvalues, in EBRs, or in atomic limits, is 4 times n, where n is an integer. Yes? Does it make sense? Okay, so now you ask, well, what are the topological states? Well, topological states are all the bands that don't have 4 times multiple of 4 eigenvalues. So if I have odd number of eigenvalues, then I'm basically back to odd number of eigenvalues. I'm basically back to what I showed you before with some caveat. It's got vowel points. But I'm basically back to like odd number of eigenvalues, right? So the interesting case that shows up here, okay, is when this is 2 times 2n plus 1 negative eigenvalues, right? I have bands with 2 times 2n plus 1 negative. So this is the interesting new case that comes in 3D, right? Odd number of eigenvalues I had in 2D also. In 3D, it's actually a Weil system, but doesn't matter. Is it clear that this is the more interesting case that sprungs up in 3D? Okay? So let's just find out what this case is. I'm going to take two occupied bands. This is the higher order of TI without time reversal. This is the Brion zone. Two occupied bands. And I'm going to take minus minus, plus plus, plus plus, plus plus, plus plus, plus plus, plus plus, plus plus. Okay? This can never be written down in terms of atomic limits, because all my atomic limits have 4 negative eigenvalues, or 8. Yeah? So this is topological. But what state is it? I don't have time reversal. Okay? If I had time reversal, this would be a Kramer's pair, and this would be what? Each of these would be Kramer's pairs. These are the occupied bands. What would this be if I had time reversal? Do you guys want lunch? What would this be if I had time reversal? Come on, you know this. A what? So if I had time reversal, there's a way of making this time reversal invariant by making these negative eigenvalues the same energy. Then what would this band be? Doubly Kramer's pair, Kramer's pair, Kramer's pair, Kramer's pair, Kramer's pair, Kramer's pair. What would this band be? Huh? You know this, and I get paid by the hour, so I'm just going to sit here until you get this. So what is it? If this is an occupied band with this a Kramer's pair, this a Kramer's pair, this a Kramer's pair, this a Kramer's pair in 3 dimensions, what is the system? You know what this is. We've been talking about this, like, in some, yeah. Let me give you a name, Kane, and so this is well, the quantum spiral is 2D, so what is this? It's a 3D TI. If I had time reversal, so if I add TR and keep the number of bands 2, occupied bands 2, this is Foucault index, right? But the moral of the story is that, right, people tell you that you break time reversal on a Foucault insulator or 3D TI, and you kill the insulating state. And that's not true, because we just proved, at least with inversion symmetry, we just proved that this thing, so if I add time reversal, this is a Foucault, but I break time reversal. I haven't added it, so this big if. So I haven't added it, and I have these inversion eigenvalues. So, and I showed you that these inversion eigenvalues you cannot write in terms of sum of elementary band representation, so this has to be topological. Okay? But people have been saying that, you know, you take a Foucault insulator, you put it in a magnetic field, and you kill the right time reversal. If you break time reversal TI, it's dead, but it's not dead. And the reason is that this is a higher order topological insulator where you'll have some corner state, well, this is a momentum space, you'll have some corner state in real space going, you know, it's the way it's going, it's arbitrary, but you'll have some corner state that goes on an inversion symmetric path around your sample. In this I drew some inversion symmetric path. Okay? So the surfaces of this system, a system of 2 bands that has this topological invariant, or that had this eigenvalue structure, that's not a sum of EBRs. Physically, what does it represent? Well, if I don't break time, if I would add time reversal, it would be a Foucault. If I break time reversal, it's still topological, because I know this topological, and what happens is that you'll have these corner states running around the system. The surfaces are generically gapped, but you have one-dimensional modes. And the way to see that is very simple, actually. So by this statement, we said that if I add time reversal, it's a Foucault index. It's a Foucault index. So let me take a sample, which is, let me take a thin, I mean not thin, still 3D, but a thin sample. So this is Chinquy-Shui's experiment. Okay, let me take a thin sample like this and add a magnetic field. This was a TI before, so I put time reversal, now I break time reversal. If it was a TI, I had the Dirac cone, here, but then I gap the Dirac cone here, and I gap it here, and I have hole conductance 1/2 here, and minus 1/2 here because of the normal is this. Because I have on one surface, I have a surface area hole conductance 1/2, the other one with minus 1/2. There's got to be an edge mode around them here somewhere, okay? And that's the edge mode that Chinquy-Shui is seeing in his experiment. And this edge mode is actually the higher order TI state, okay? So even if I break time reversal, you have an edge mode in a TI, okay, running around the sample. And that edge mode is a gapless mode, so it has to come from some topological structure. And this is a higher order TI. It's the simplest example. So a TI plus time reversal breaking is not trivial if you have inversion symmetry. Okay, so just to make some, okay, so I'll just to make some shameless, yes. Sorry? Well, this is not two-dimensional because this is still macroscopically 3D. Sorry? Yeah, but it's a 3D topological insulator with one-dimensional modes. So that's the point. So it's a 3D. So you can think, you can think of the surface of this guy as being a TI. You can think of it's a 3D that's got gap surfaces, but the surfaces are not trivial. The surfaces are topological themselves, and they create. And they're topological. This surface is related to this one by inversion, and that's what basically flips the normal. This is why this is 1/2, this is minus 1/2. And you get this edge mode around, and of course you can, by imperfections of the sample, or by you can guide this mode to go like this if I want to. The way the mode is going is not universal, but between two surfaces related by inversion, you have an edge mode. But this is a 3D. Now, if you make the slab very thin, you cannot get the same thing. No. If you make this slab very thin without adding magnetic field, you cannot get the same thing. Right? So if I make a 3D TI and make the slab very thin, then this upper surface is going to communicate with the lower surface. The Dirac points will gap, and I'll get 0 hole conductor if I don't add a magnetic field. Right? Not if I don't add a magnetic field. If you add a magnetic field, to have one-dimensional modes, they've got to be chiral, right, in this. Right? So if I take a TI, there's actually one-dimensional modes that are not chiral, which is the higher order. If I add time reversal and I have this, I don't have time to go through it, but if I have this with time reversal, 2 Kramer's pair with minus, and the rest just pluses, this is a higher order topological insulator with time reversal that's got helical modes running like this, not just chiral. But these are 3D systems. Okay, so that's it, I think. Thank you.
Okay, Thank you, Andre, for that very nice talk. If there's any quick question, really quick question, we can take that now. There's one quick question.
Yes.
Here.
So your statement that anything that is not band is topological.
That is not what?
That is not band.
There's
that
not
doesn't come from band.
anything that's not an elementary band representation. Yes.
It's topological.
Yes.
Does it hold in the presence of correlations?
Well, depends how you define band. Then in the presence of correlations, you don't have the single particle states at the K point. So normally any of this would go away. But there's still some indices. For example, the overall, if I take inversion, that statement will hold in the presence of inversions. And so instead of having minus, plus, 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 the eigenvalues at high symmetry points, you can define an index, which is the product of the eigenvalues. And that's just the eigenvalue, the inversion eigenvalue of the many-body wave function. And that will hold.
It becomes many bodies.
That's right. So there's some parts that hold, there's some parts that don't hold. Which hold and which don't hold, I don't know.